Now let's see some examples. Okay, now we have this signal del of t. So we already found out what is the Laplace transform of del of t. So what is that? So del of t e power minus st dt integral minus infinity to infinity. This is equal to just 1. Okay, and what is the ROC? ROC is entire S plane. Okay, and there are no poles and no zeros. Okay, because there are no poles and no zeros, how does the transfer function look like? The transfer function is just a straight line. We plot it. Okay, so this is what we call as the all pass filter. It does not do anything to the signal, it just passes the signal as such, and it converges everywhere. So it doesn't matter what is the exponential that you're feeding in, it will just produce it as such. Now let's try and find out the Laplace transform of cos omega t u of t. So what is cos omega t u of t? You can rewrite that as Laplace transform of, you can rewrite that as e power j omega t plus e power minus j omega t by 2 into u of t. But we already know what is the Laplace transform of e power minus a t u of t. That is nothing but 1 by s plus a, right? So in this case, when we try to compute the Laplace transform using that formula, what would you get? You would get 1 by 2 times 1 by s plus j omega plus 1 by 2 into 1 by s minus j omega. So the first term actually gives minus j omega, the second term gives plus j omega. In other words, this is half of s plus j omega into s minus j omega of s plus s minus j omega plus s plus j omega, which is equal to s by s square plus omega square. So this is the Laplace transform of the expression cos of omega t u of t. Now what is its ROC? So the ROC here is, we have used this expression, and then here we have said the ROC is actually the real part of s should be greater than minus a. So now we have added two terms, so we have to take the intersection of the ROC. So the intersection here is, so for this part, the real part of s should be greater than minus a, where the real part of a, basically you have to consider the real part of a, and the real part of a here is plus or minus j omega, which is equal to 0. So the ROC here is real part of s which is greater than 0. So if you draw that, you just get the entire right half plane. And where are the poles? We have two poles here, one at plus j omega, another one at minus j omega. Okay, this is plus j omega, and then another one at minus j omega. And where is the 0? There is a 0 at 0. Okay, this is s minus 0, right? So the ROC here is to the right of the rightmost pole, okay, and it includes the j omega axis. It's to the right of the rightmost pole, and hence this is a causal signal, okay, and the real part is greater than 0. So because the real part is greater than 0, it does not include the j omega axis, and hence this is not absolutely integrable. This signal, if you try to compute the integral of the signal mod of cos omega t from 0 to infinity, it's not less than infinity, right? So this is not absolutely integrable, and hence the system if this is the transfer function of some system, then it is not a stable system. So we can tell so many things about this just by remembering this one formula, right? So if you remember this one formula and the properties of Laplace transform and the concepts, we can identify so many things about the system. Now the Laplace transform of this signal is going to be even easier. We are not going to compute any integral. So the power of properties is this. Now we are not going to even to touch to evaluate any integrals, because we know that if there is a shift in the Laplace domain, then the corresponding time domain actually has a multiplication, right? So here in the time domain we are multiplying with e power minus at, so which means in the Laplace domain there should be a plus a, right? So we already have the Laplace transform here. All we need to do now is just replace s with s plus a. So the Laplace transform of e power minus at cos omega t u of t is just s plus a divided by s plus a the whole square plus omega square. Now what happens to the ROC? The ROC is now shifted with a. If a, we assume that a is a real number, okay, so the ROC gets shifted by a. And what happens to the poles and zeros? Now there is a 0 at minus a. Now there is a 0 at minus a, okay, and where are the poles now? And where are the poles now? So as you can remember, you can just simply replace s with s plus a here directly. So if you replace there, we will get that this is s plus a by s plus a plus j omega times s plus a minus j omega, which means the poles are now going to be present here, a plus minus a plus j omega minus a minus j omega. So those are the poles, and the ROC was shifted by a, and it is shifted to the left side because we have a minus a, right? So now the ROC here looks like this. Now can we comment about the system? The ROC is right of the rightmost pole, so it is causal. Obviously these signals are causal, so we know that if this is the impulse response of a system, it has to be causal. Now what about the stability? This includes the j omega axis, so the system becomes now stable. So the addition of the e power minus at term, where a is greater than 0, makes the system actually stable. Now let's find the Laplace transform of a signal which is e power minus mod t. So in other words, evaluate e power minus mod t, e power minus st dt. So what is this? This is nothing but integral minus infinity to 0 e power t e power minus st dt plus 0 to infinity e power minus t e power minus st dt. So in other words, we can say that this is equal to the Laplace transform of e power t u of minus t plus the Laplace transform of e power minus t u of t. Okay. So once again, we don't have to evaluate this. We already have done this in a previous exercise. It is 1 by s plus 1, and we have minus 1 by s minus 1, right? And what is the ROC for this term? The ROC for this term is the real part of s should be greater than minus 1, and the ROC for this term is that the real part of s should be less than plus 1. Now, what is the combined ROC? The combined ROC is the intersection of these two regions. The region that is greater than -1 is this side, and the region that is present on less than +1 is this side. So, our final ROC is an intersection of these two regions, which is a strip, and that exists between -1 to +1. And what are the poles? The poles are precisely the borders, which is -1 and +1. So, these are our poles. So, do we have a 0? We can check that. This is s minus 1 into s plus 1 times, which is equal to -2 of s square minus 1. So, we do not have a 0 here, we just have 2 poles here. The system is not causal clearly because we have a rational transfer function and the ROC is not right sided, which makes the system non-causal, and that is clearly evident from its impulse response, right. So, if this was the impulse response, then the impulse response actually exists on both sides of the time like this. So, it clearly has non-zero values for negative values of time. So, this is definitely not a causal system. So, is it stable? It is definitely stable because the j omega axis now is part of the ROC, and that makes the system stable.